Okay, the next talk is Misha Lyubich. Sorry. He is going to talk about structure of Feigenbaum Henon maps.
Thank you. Well, thanks to the organizers for the invitation. So I'm very happy to be back here. Does it work? I just press. Works now? Okay. Well, so it's first time after pandemic, so it's lively meeting, so I'm very happy to be here. And so I visited IMPA first time more than 30 years ago. It was 91. And at that time, I met Marcelo first time. So he was a little younger, but still recognizable. So, and and then I kind of have visited IMPA many, many times, maybe more than all other places together, and have been watching how the place has been flourishing through these years. And of course, Marcelo played a very instrumental role in that. So it is. So congratulations at you. Okay. So and I will be talking about the structure of Feigenbaum Henon maps. So, and what I plan to do is to give some overview of this direction of research, which has been quite active over the past 20 years, though there were still few practitioners in this area, and there was not much attention paid to it from outside. So let me try to make a little advertisement today. Okay, so the general idea is, so we are dealing with real analytic or complex analytic dynamics for that matter, and we understand pretty well what is going on in dimension 1 in both areas, and we want to sort of to perturb this one-dimensional situation to two-dimensional. So in the one-dimensional situation, the best understood family is the quadratic family, real or complex. We want to perturb it, just slight perturbation, to the Henon family from just this degenerate parabola to a little bit thickened parabola. So it does not seem to be a big deal. So in formulas, so we have quadratic family, and then we have two-dimensional quadratic family, so of Henon maps, also given by these simple equations. So the first occasion, I think, of this kind of perturbation occurred like about 30 years ago, maybe a little more. It was the Benedict's and Carlson theorem, which pushed the Jakobson's one-dimensional theory to the Henon family. So Jakobson's theory tells us that in the quadratic family, there is some abundance of the stochastic parameters. These stochastic parameters form a set of positive measure. And so Benedict's and Carlson so just thickened this theorem a little bit, so and prove a similar result in the Henon family. That is what Michael was talking about so a few days ago. And of course, for someone who is not familiar with the area, it does not look like a big deal. But so Carlson mentioned once that it is the most difficult analytical problem that he had ever dealt with. So it is Carlson. So for him, it was the most difficult analytic problem. So it is really a very, very non-trivial, very deep technical development. Not fully understood, far from being fully understood, even today, so 30 years later. Well, so this theory, so in one dimension, can be upgraded to a regular O-stochastic. Yeah, by the way, so before I go further, so I should say that, of course, Marcelo made further important contribution to this Benedict-Carlson theory. So he showed that this kind of phenomena appeared everywhere. So whenever we have a homoclinic tangency, and it happens all over the place in the bifurcation locus, then we will observe this Carlson-Benedict attractors. And he actually proved with Michael that this attractor so is a global attractor, so attracts so almost everything in the space of the Henon map, and it is still very surprising result. So because it goes beyond somehow what is controlled, so what is controlled by one-dimensional perturbation. Somehow you need to understand so many things that just randomly emerge in this two-dimensional world. So I think that it is this theorem of Marcelo and Michael needs to be understood better, at least as I'm concerned. So now we can just upgrade one-dimensional theory to regular or stochastic dichotomy that I proved some time ago, and which says that in the quadratic family, so in this quadratic family, for almost any parameter, the corresponding quadratic map is either regular or stochastic. And the former means that it has an attracting cycle. This map has an attracting cycle which attracts almost all orbits. And stochastic means that it has an absolutely continuous invariant measure which governs the behavior of almost all orbits in the sense of ergodic theory, Birkhoff, so Bohm-Sinai, SRB measures. So we have this clear picture. Actually, this picture was refined later in an important way by Gugu and Artur, who upgraded stochastic to Caille-Ekman, which is a very important refinement of the result. So now we can ask whether this kind of dichotomy, which is kind of satisfactory description of the dynamics from Kolmogorov's probabilistic point of view, whether this can be pushed to this Henon perturbation. And then we enter in the world of the police conjectures. So it's some attempt to understand typical behavior of typical dynamical systems from this probabilistic point of view. So, and in this particular situation, it would mean that for a sufficiently small Jacobian, so we may anticipate only finitely many attractors that govern behavior of almost all orbits. So, well, it is a dream problem. Maybe finiteness should be upgraded to countably many, so I don't know. So it would still be a very good result, a very good understanding. But this problem is far from being approachable at that time and this time. And so today I will go to kind of much simpler class of maps, which is zero entropy situation. We know that zero entropy is sometimes more difficult, so most difficult, but in this situation, so zero entropy is a kind of more tractable and better control can be attained. Okay, so and that will be what this talk will be about. And let us start from the beginning, from the one-dimensional model. It is one-dimensional Feigenbaum maps, which means unimodal maps. So for us, it most will mean, so how does it work? Unimodal maps, one critical point. We assume that the critical point is not degenerate, at least mostly for this talk, we'll assume that. And it is infinitely normalizable. So for instance, in the Dublin case, we have two intervals which are permuted by dynamics. Inside of these intervals, we have four intervals, cycle of four intervals permuted by the dynamics, and 8 intervals, etc. And the intersection of all these cycles produce for us an odometer, or an attractor, Feigenbaum attractor, which attracts almost all orbits on the interval. So it is quite a clear situation, and of course we can just replace here, Dublin with Striplin, or whatever you like, whatever period you like, whatever combinatorics you like most. And this kind of parameters are created through cascades of Dublin bifurcations or Triplin bifurcations or whatnot. And there is very remarkable fundamental phenomenon discovered in the mid-70s by Feigenbaum, dependently Collet-Reser. So it is universality phenomenon. And so there are two parts for this universality phenomenon, dynamical part and parameter part. And dynamical part says that if you have two infinitely normalizable maps like that, so with the same combinatorics, not necessarily quadratic, you start with unimodal maps which are infinitely normalizable in this sense, and with quadratic critical point. And so If, so they are this kind of maps, because we assume combinatorics is the same, they are topologically equivalent, but it turns out that the counter set, this odometer, which controls the dynamics, has a much better geometric property, geometric virtue. So it is preserved not only topologically, but geometrically. So the conjugacy between such two odometers is smooth. So the small-scale geometry of these odometers is asymptotically universal. It does not depend on a particular unimodal map in question. It is what is referred as the dynamical universality, and there is a parameter universality that if we go through the cascade of Dublin bifurcations, here this cascade is indicated, this cascade of Dublin bifurcation, familiar picture, then the convergence to the limiting parameter happens at the universal exponential rate. So this lambda, the rate of convergence, is universal. So in what sense? Well, you can consider various unimodal families, so different generic unimodal families which entertain these cascades of Dublin bifurcations, and then the rate will not depend on the family you have selected. So that is two fundamental universality properties which at that time took people by surprise. And then there was an amazing physical explanation put forward by Feigenbaum and Collet-Resser. It was so this became known as a renormalization conjecture. So everything can be explained in terms of the renormalization operator in the space of unimodal maps. So in the Dublin case, we are just dealing with the second iterate of our map, restricted to the central interval, to this interval of period 2, and rescaled. And this is some transformation partially defined in this space, defined in the space of renormalizable unimodal maps. So it's some partially defined operator in the space of unimodal maps. Here is a schematic picture of the space of unimodal maps, some big infinite dimensional space. And the conjecture suggested that in this space we observe a unique fixed point, f star, and this point is hyperbolic point for our renormalization transformations, hyperbolic point of index 1. So the stable manifold of this point has codimension 1, unstable manifold has dimension 1. And so if we have such a picture in place, then the stable manifold controls the dynamical universality, it controls the small-scale structure of all infinitely normalizable maps. It consists of infinitely normalizable maps and controls its small-scale structure. It tells that it's asymptotically the same as the small-scale structure of this fixed point. And parameter universality controls this universal scaling laws. For instance, in the quadratic family, here schematically depicted like this curve, this quadratic family. It is just curve in our space, in our functional space. And the scaling will be the same as in the unstable manifold. Unstable manifold is a universal one-parameter family that controls all other parameter families. So in the case of Dublin bifurcation, it was first established by Lanford with the computer assistance, and then there was some conceptual development, which ended up with the full theorem for Dublin and for all stationary combinatorics. Today we'll play only with stationary combinatorics. Let us assume that on all levels we apply the same renormalization transformation. It could be Dublin, it could be tripling, but we just repeat it all the time in all scales. And so eventually, for arbitrary combinatorics, it was established in the series of works by Solomon, Macmillan, and myself. And then it was sort of ultimate refinement of the proof. So in the work of Artur Avila and myself, so based on Artur's idea of Caratteadori metrics, that Caratteadori metric is the right hyperbolic metric, like what Carlangelo described in the last talk. It is important to have metric which is naturally contracted by the map, and so in this case, that was the one, and it brought the proof to the ultimate form. Okay, so since that is all I wanted to say about one-dimensional situation, and now we want to perturb it to the two-dimensional. So we want to perturb it not necessarily to the Henon family, though it is our main case of interest, but it could be some space of Henon-like families. It is, well, it's important to consider so big space of Henon-like maps, like quadratic-like maps in the one-dimensional situation, because the renormalization acts in these big spaces, not in the small finite parameter slices. So this kind of situation, actually, so Charles just mentioned for me just before this talk, he mentioned that that already in their original paper with Coulet, they observed this, they already sort of made public this observation that there is some universality features in this Henon family. So that still two-dimensional world somehow also entertains this universality feature. So there should be some renormalization machinery behind that. And actually there was this one-dimensional development followed up with some physical experiments, some computer experiments, with systems from infinite dimensional systems from fluid dynamics, and in many of them, somehow there was the same observation that somehow, of course, not always, but it depends on the universality class, also on the nature of the system, of the class of system, but still many systems that surprisingly entertained the same universality structure as a Feigenbaum-Collier-Dresser situation. Okay, so that is indication. So, well, there should be some good renormalization theory for the Henon maps, so for this easiest, sort of smallest perturbation of the one-dimensional quadratic maps. And there was some development already in the 80s. It is Koch who justified actually the universality of the period doublings. So period doublings. So they created the normalization scheme, Petop normalization scheme, which justified universality observed in the Henon family for the doublings. Then there was this work also in the late 80s, this work by Gambourdeau, Van Strien, and Charles Dresser, so who observed that the odometer, this attractor, in one dimension survives small perturbations as long as the map is infinitely normalizable. So if we keep the map infinitely normalizable, Henon map Z, then the odometer survives. And then already like 10 years later, no, not 10 years, about 10 years later, a little bit more, so André de Carvalho, Marco Martens, and myself, undertook some systematic analysis of this situation, and there were some features that we anticipated, and there were some features that surprised us, and I will tell you this story. That is what I want to do. So I will, for a good part of the talk, for at least one half of the talk, I will follow this work by De Carvalho, Marco, and myself. So here is an indication, so how this normalization, doubling normalization, so the regions can appear. So you have something bounded by stable manifold or fixed point by unstable manifold. And then for certain parameters, this region can return back into itself as a Henon-like map. And so it is a normalization. And then you can repeat it. And so, and you are interested in some small-scale features of this normalization procedure. So, so the way we started to deal with that was not like that, because it requires some a priori control of the stable and unstable manifolds. Instead, we took a geometric perturbative approach. So the map is small perturbation of the one-dimensional map. So we have the critical point, the critical value of the one-dimensional map, and so we can renormalize, renormalize Henon-like map. Oops. So Henon-like maps, we can renormalize. So sorry, one is sticking. Oh, I went very, very far. Where did I go? You now see the whole talk. I don't need to say anything anymore. Where did I go, son? Let's see. I see. You already see for the reason. I see that I'm pushing the wrong button. Okay, sorry. Okay, here it is. Here it was. Yeah, I think that's what it is. So we have so in one dimension you can renormalize. Traditionally, the most popular place to renormalize is near the critical point, But you can go to the critical value as well, is a matter of convenience. So you can go to some other places of your odometer and renormalize there and see what is going. So develop a similar theorem in some different places. And so in this Henon case, we selected critical value, found the critical value most convenient, so it is the tip of our parabola, of our Henon parabola. And here we built up certain box, specifically in geometric way. It is perturbed one-dimensional map, so we have some geometric construction of some box, which under the second iterate comes back. And then we make certain change of variable, which is non-linear change of variable, but it is very specific, concrete change of variable, which brings our map to its original normal form. So remember that the normal form was our favorite normal form, is like that. So here the second coordinate is x. So it's and so the perturbation is controlled by this unimodal map f of x, unimodal map f of x, and this small perturbation epsilon, small two-dimensional perturbation epsilon of xy. So we bring this to this form, and so if it happens to be, again, renormalizable, we can repeat it, make change of variable, we obtain second renormalization, and so on, go on and go on. And so the question, so whether we can justify in this situation the universality picture. And the main lemma, so for this justification, tells us it's very natural, something that you would anticipate, because you're dealing with strongly dissipative map. If Jacobian original is some delta, then under the renormalization, Jacobian becomes delta squared, so you anticipate that the map is pushed down to the degenerate one-dimensional slice. So you have here some schematic picture of the space of Henon maps H, of the slice of unimodal maps. In this unimodal slice, we see the normalization picture, stable, unstable manifold. And so the Henon maps pushed under normalization to the slice in the super exponential rate. So that is, so one can be very specifically justified with this renormalization, with this geometric renormalization scheme. And it implies that this hyperbolicity can be extended from the unimodal maps to the Henon maps, and actually the transversal direction corresponds to the zero spectrum. So everything in the transverse direction is pushed down to the unimodal one in the super exponential rate. And the fixed point is the same one-dimensional degenerate fixed point. It is supposed to control small-scale structure of the dissipative Henon maps. And the unstable manifold is the same one-dimensional unstable manifold. Of course, the stable manifold will be extended a lot with the infinitely normalizable Henon maps that will form a codimension one submanifold. Okay, so that was somehow justification, and one of the consequences is that we recapped the result of Collet-Ekman-Koch. So with this scheme, that there is this parameter universality. So in the space of parameters of Henon maps, so we have C parameter, Z squared. So C parameter, it is parameter of the one-dimensional quadratic family, and we have B parameter with the Jacobian parameter. And we have through Feigenbaum point, Feigenbaum Collet-Reser point, C star, there is a curve, analytic curve, which goes up, and it is approximated with bifurcation curves corresponding to Dublin bifurcations, so which have uniform size when we approach this curve of infinitely normalizable parameters. And so if we slice now on certain level, if we slice this picture, so slice this picture, so again, I'm in trouble.
Are these curves uniquely defined? Hello, Miss. Are these curves uniquely defined? The ones to the CNs are the super attracting points, or which
so
parameters are those?
super attracting node, you can use parabolic, for instance, and then they will be uniquely defined.
The
so
curves going
the curve going up. So the bifurcations happen in parabolic points after all. So these parabolic points, super attracting would not make much sense.
Right. Yes.
But parabolic is good.
Okay.
Okay, so there is this parameter universality. So and how, so and the rate is the same, of course, as in the one-dimensional situation. So because it is controlled by the eigenvalue in the unstable direction, and the unstable manifold is just the same. And so what about dynamical universality? Here is the result of this type, so that we have pretty good understanding of the shape of this n-fold normalization of our map. So it is, first of all, it is one-dimensional approximations, Fn, which converge exponentially fast to normalization fixed point, these approximations. Then we have this b to the n, which is, so, geometry, yeah, okay. So b is the average Jacobian, our main geometric parameter today. Average Jacobian on the odometer. Average Jacobian on the odometer, it is b, and so the average Jacobian for the normalization will be this power of b. And then, so it would look exactly very similar to the Henon family, except that here we have also some universal function a of depending only on x, and up to exponentially small error. That is the shape of our map. So it was a good news somehow, though a little bit boring. So we anticipated that everything, once we have this normalization picture, that then everything should work exactly similarly, exactly in the same way as in one-dimensional situation. We would have parameter universality, dynamical universality, and can develop the whole theory smoothly, but not so fast. So Henon maps always keep some secrets and some surprises. So what we realized sometime later, so after a lot of suffering, that actually the geometry of this odometer is not necessarily bounded. So bounded geometry means that we have a Cantor set created through the two pieces and two pieces inside of the previous two, and two pieces inside of the previous two, etc. And bounded geometry would mean that somehow this configuration of pairs of pens, one piece and two pieces inside, on all levels, these configurations stay uniformly bounded. Geometric, they are, say, quasi, roughly by, say, roughly equivalent, by Lipschitz equivalent, say, to some standard configuration. That would be bounded geometry. And we realized after some deliberations that it did not happen, does not necessarily happen, and actually typically does not happen in the later paper with Peter Hazard, who is here. So we show that, so for almost all parameters in generic one-parameter families of maps, as long as the average average Jacobian changes, then we observe unbounded geometry. It is related to this crashing phenomenon. So somehow, for a normalization, we have geometry which is fully controlled by one-dimensional maps. So we have something that we understand very well. But then we go back to the original plane. We do change of variable. And then two of these pieces can be put, so with certain choice of parameters, they can be put one exactly above the other. And then when we iterate Henon map, spreading this around, then we crash one into another, making a gap in between them much smaller than, much tinier than the size of the pieces. This creates unboundedness of geometry, and that is what typically is observed. Actually, I don't think that until now there is any single example of these infinitely normalizable Henon maps for which the odometer has a bounded geometry. I don't think that there are examples, though. So long ago, like 30 years ago, people anticipated there are some papers on exactly this kind of maps. So the infinitely normalizable two-dimensional maps with bounded geometry. So we don't know whether such examples can be constructed for Henon maps. At least it is a delicate problem, obviously, because typically we observe a different situation. And moreover, so in the one-dimensional situation, we have this parameter rigidity. The odometers, different odometers are smoothly conjugate. Here they are not. Here, if we change Jacobian, then the geometry of the set will change exactly for this reason. So that is the underlying reason, because the Jacobian will sort of affect the geometry, different Jacobians affect geometry in a different way. And there is some bound on the Hölder exponent of this conjugacy. So this conjugacy cannot be better than that much Hölder. In particular, if we try to conjugate our odometer to one-dimensional odometer, then the exponent would be at best 1/2. So that is a kind of bad news. That is bad news. So we now understood phenomenon correctly, but we were not quite happy about that because somehow, so we hoped naturally that really this phenomena should survive extension to higher dimensions, and so should have some physical meaning and significance. So. Yes, it is on the attractor, yes. On the odometer. Odometer is the attractor. So what happened next is that, Mikhail Feigenbaum, who was still around at that time, he looked at this result. He was surprised. He did not anticipate that. And he started to do computer experiments. And at some conference, he showed us his computer experiment. He gave a talk on his computer experiments, which definitely indicated that still geometry must be universal. So in most places, somehow you need to look very, very carefully to find those places where geometry is broken, so where geometry loses these universality features. So it gave some conjecture to think about. And sometime later, with Marco, we indeed confirmed this Feigenbaum's conjecture. So by showing that in the probabilistic sense, so the geometry is universal. So the geometry of this unique measure on the odometer. So odometer has this minimal unique ergodic dynamics. And so there is a canonical measure, mu sub f. And if we take the set of measure 1 minus epsilon, carefully selected set for any epsilon, then so the corresponding conjugacies between two odometers will be 1 plus beta smooth. So like in one-dimensional situation. So typically, somehow, in typical places, you would not observe this violation of the universality. And in particular, the Hausdorff dimension of this canonical measure is universal. I believe that it is a kind of this result should be kept in mind for people who are trying to do renormalization in higher dimensions, because somehow that is the way how universality, at least dynamical universality, is going to survive. Again, this Kolmogorov's probabilistic point of view is the one to follow. And this fantastic one-dimensional universality does not survive extensions to high dimensions per se, but it does in this probabilistic sense. Okay, so that was good news. That was good news. So you see this oscillation between bad and good news. And now another phenomenon that was not maybe so surprising for people who understood two-dimensional dynamics, topology of two-dimensional dynamics, but also for us it was somewhat surprising, and also goes against one-dimensional intuition. So we had spent a lot of years just with one-dimensional maps, so tried to apply one-dimensional intuition, and every time, so we had realized that we had to be very, very careful with that. So in one-dimensional situation, all these infinitely normalizable maps are in the same topological class, actually in the same quasi-symmetric class, so better than topological. All of them are topologically conjugate with certain regularity. Well, on the odometer, this regularity is just amazing. It is smooth, but so outside of odometer, still we have quasi-conformal regularity. So what happens in our two-dimensional extension? And the picture is the following. If we change Jacobians, then we change topology. So somehow the maps are not topologically conjugate. Infinite normalizable maps are not necessarily topologically conjugate. And definitely the topological class changes when we change this average Jacobian B. And so what where this phenomenon comes from, it is from the heteroclinic tangencies. So you say you go to some level, take a fixed point, so it has an unstable manifold, and look at the stable manifold which it is tangent to. So go to deeper level, some deeper level K sub n, and consider the stable manifold, and so try to find the one which is tangent or almost tangent to that one. And so this kind of tangencies happen when you change Jacobian, happen in certain rate, which we understand due to our normal form, due to our universal normal form for the renormalizations. And so we can write down the simplest equation. So the scale here, on the other hand, will be sigma to the power 2 to the k, where sigma is the universal scaling factor from dimension 1. And on the other hand, so this manifold will move forward with this speed. So in this scale, b to the power 2 to the n. So they should coincide in order to create this tangency. And it allows to recover this Jacobian. So you see that log b over log sigma is equal to this kn, this level kn to the power divided to the power 2 to the n minus 1. So this topological invariant so controls the geometry, the average Jacobian. So the average Jacobian can be recovered. So it is this kind of rigidity that, of course, is absent, is not present in one-dimensional situation, but so that is what is happening in two-dimensional, specifically in two-dimensional situation. And so we analyze this a little bit further. These pictures are related to the problem of density of hyperbolicity. So we know that hyperbolicity is not dense. That is old disproved conjectures. But however, this conjecture could still be valid in zero entropy region. And that is what is confirmed by this picture. So we have the theorem with marker, again, that in some narrow strip, so for very small Jacobians here in the Henon parameter family, in the zero entropy region, so up to our unstable manifold, up to our, infinitely normalizable curve, gamma star, so we have dense set of Morse-Smale, so open dense set of Morse-Smale systems. And the curves which divide these into cells, these curves are curves, this is curves of heteroclinic loci. So that is where heteroclinic tangencies occur and where the topology changes. But the web is still quite non-trivial because it is not locally finite. Since stable manifolds can accumulate one onto another, these heteroclinic loci also can accumulate onto one onto another. So we have quite a complicated web here in the zero entropy region. However, so the hyperbolicity, Morse-Smale systems are still dense. So it seems that somehow one can pursue still this problem of density of hyperbolicity, so in higher dimensions, at least in zero entropy regime. Okay, that's one confirmation of it. So let us see. Now I cannot. So it rotates when I don't want, and it does not when I want. So now let us move for a moment to a complex situation. We can consider also complex Henon maps. This theory was originated in mid-80s here in the work of Milner, Friedland, Hubbard, Haberstworth, Bedford-Smiley, Farnash-Sibani, and then there was quite an interesting development over the years, but it looked very, very different from the real theory, or complex one-dimensional theory, because these theories somehow have a fine distinction between different parameters. And the theory that was developed in the complex world was more or less universal. So just all parameters have the same the same structure, some certain currents, certain measures, so the equidistribution results, everything looked very homogeneous, except maybe for some perturbative results for hyperbolic maps, then for parabolic maps, but that is it. So there was no this a sort of developed perturbative theory in this situation. And that is what we undertook with Arthur. So we realized that this result somehow should be valid quite a while ago. Namely, so we constructed some special Julia sets of positive area. It was not first examples. First examples were due to Buff and Shirita, but our examples were of different nature. And our examples are exactly this Feigenbaum-Collet-Resser type. So they are infinitely normalizable with very well-controlled geometry. And it looked so natural that they should be amenable to perturbations. And so that is what we did. So let me just mention that somehow this result of in dimension 1, this result in dimension 1, so where should I go, is based on some random walk, renormalization random walk. You go from scale to scale, so, and you look, so which trend dominates, whether to go from shallower scales to deeper scales or to go from deeper scales up to shallower. And if the going deeper dominates over going up, then you observe a Julia set of positive area. And it is very well quantified in our work with Arthur, and then we were able to produce example, real actual example of this type. So that is kind of picture of this example that we call black hole. So this race, this red race, is a race of escaping orbits. You see they're very, very thin. It's very difficult to escape. Much easier to stay in the Julia set. So, and then we somehow produced a perturbation and Henon perturbation of this example of the Julia set. We showed that says nearby there are infinitely normalizable complex Henon maps, for which there is this odometer will survive, of course, this perturbation, but it will now serve as a kind of wild attractor for this perturbation. Namely, if we take the forward Julia set J plus, so you can guess what it is, it will have positive volume, will be four-dimensional volume, and almost all orbits there will go to our odometer, but topologically generic orbits will go to some little Julia set J. So inside of J plus, there will be some topologically transitive Julia set J. I don't have time to define all these guys, and I even can point correctly towards them. But anyway, in this J plus, so positive volume is pulled towards the odometer, positive volume is pulled towards odometer, and generic points topologically are pulled towards the bigger transitive set, which is called J. That is the situation which is called in our field the wild attractor situation. So, and that is what can be observed in the Henon family, in the complex Henon family. Yeah, that is what is written here, and kind of the rough idea is that this renormalization random walk scheme survives under perturbations, and so that is what easy to believe, and which can be actually justified. So another situation. So I think that I'm running out of time, so I will just list some other developments. So other situation is the analogous phenomenon in the real world. So it is now non-renormalizable. It's different type of maps which are non-renormalizable in the usual sense, but which are infinitely normalizable in some generalized sense. It is so-called Fibonacci maps. And so in mid-90s, Brun, Kerr, Nowitzki, and Van Strien showed that if to take such a map with sufficiently big, with a big criticality z to the d, then it exhibits wild attractor. So the behavior of probabilistically, the behavior of orbits will be different from topological behavior of typical orbits. So, of course, it is very natural to try to perturb this situation as well, and to to construct such an example in the real quadratic family. But there are several issues here. So one of the issues you see that you should go to the high degrees, and Henon family is a kind of quadratic Henon family, but there is some machinery developed by Gonchenko, Turaev, Shilnikov, and Kaloshin. And actually it was Vadim who drew my attention to this phenomenon, and which prompted the whole this project. So that in the quadratic Henon family, one can create high-order tangencies, so one can degenerate to the maps, unimodal maps with of high degree. And so that would be one ingredient. Another ingredient which is not fully developed, so Daniel Smiley developed some good piece of it, but we need a little bit more. So it is renormalization theory for Fibonacci maps. We need this renormalization, hyperbolic renormalization fixed point of the high criticality Fibonacci map in the space of multimodal maps in order to extend it to Henon. So there are several issues to deal with, and also there is an issue that in this case it's very important that you renormalize. If you renormalize near a critical point or critical value, you fail. You need to renormalize in a very smart way. Artur has found a place where you should renormalize in order the Henon perturbation to survive this kind of renormalization, in order this renormalization to be robust under Henon perturbation. So it is not finished project, so that is kind of theorem in quotation marks. So, but we are optimistic that it can be done. And let me finish just with the two slides. So it is an attempt to build up non-perturbative theory, but axiomatic. So to put some axiom, what does it mean to be infinitely normalizable Henon map unimodal? What does it mean to be unimodal? And it is something that we have been developing already for several years with Sylvain Crevissier, Enrique Pujalis, and Jean-Guk Yang. And so we need a notion of the critical point for Henon maps, and this kind of ideas, they go back to Carlisson, Benedicts, then Bedford Smiley, and many people gave a thought to it, and in particular Enrique and Sylvain gave a thought to it, and somehow revisited it from the point of view of the Pessin theory. And that's exactly the point of view that we are pursuing here. So critical point, it is the moment when the neutral regime, so backward neutral regime, is swapped to the contracting forward regime. So when you go from critical point to critical value, of course, all these are not classical critical points or critical values, but that's what one should think of in the Henon case. So here you have backwards neutral regime in our situation of infinitely normalizable map. Forward, you have contracting regime with a certain rate, so everything should be very specifically quantified. That is the critical point. And one can define, so one can require such a critical point to be unique and to be of quadratic type in a natural way. So it's a stable and unstable manifold, stable and neutral manifold. Well, stable and the image of the neutral manifold should have a quadratic tangency in this place. And okay, so the last slide, so we have developed this under these assumptions of unimodality, that there is only one critical point of this type, and outside of the orbit of this point, or some specific neighborhood of this orbit, we have a kind of Pessin type regime, hyperbolicity controlled by Pessin boxes. So that is the theory. So we have sort of three types of pictures. It is either Pessin picture on the left, or some tunnels near the critical point and its preimages, or this channel, or this crescents, I should say, so near the critical value and its images, and everything is covered by, the whole odometer is covered by these three pictures with very well controlled geometry. And so our result is that it's also in progress, but it is in a good shape. It is in a good shape. It says that within this piece, within these tunnels, crescents, and boxes, the odometer is linearly ordered. So it is by stable manifolds. It is linearly ordered by stable manifolds. So it is essentially one-dimensional situation. It can be projected in a controlled geometric way to the one-dimensional picture. And then we can employ the Danjois and Schwarzer machinery, so to prove a priori bounds and to conclude that this kind of unimodal Feigenbaum maps belong to the universality class of the fixed point of the Collet-Resser fixed point F star. So that is where we stand now. So probably the theory is not difficult to extend it to multimodal maps, so with finitely many non-degenerate critical points. And then the dream result would be that this is generic. So in the space of infinitely normalizable maps, it is a generic situation. And I'm abusing my time, but that is the last slide with further reading. So there is some work by, so you can see, so it is self-explanatory. Let me just mention that there is a, so there is a parallel development which sort of follows up our theory, but so in a different situation. It is perturbation theory for one-dimensional circle maps, Ziegel maps, and Hermann maps. So here, these parts, there are already several people involved. It's led by Jan Polsky. Jean-Luc Young has been actively involved in that, and it allows to create very interesting, real and complex perturbative objects as well. Okay, so I guess I am sorry to abuse my time. So many happy returns, Marcelo. So thank you.
Okay. Before to initiate the questions, I would like to remember you that in 50 minutes after this talk, we have another from Arthur and Lorenzo talking about on the work of Marcelo Viana. Please stay here, okay? So, any comments or questions?
So I just wonder, you have this result that close to the Feigenbaum guys, you have density of the Morse's mail.
Yes.
So this is like uses the one-dimensional setting, or is a different kind of argument?
It is very different. Somehow it is very different. So it is heteroclinic analysis of this heteroclinic loci. So we just show that if on some domains there is no heteroclinic tangencies, well then it is Morse mail. So we need to show that it is nowhere dense, but because it is zero entropy situation, then one stable manifold can accumulate only on other stable manifolds, so it is controlled situation, and we can justify. It is very completely different from one-dimensional.
I see. And in the case of the, is there any hope to have so you have the base of attraction of the attractor, right? So a lot of points converge to the attractor. So can you say something about is there a conjugacy outside the attractor? If you can say something about the regularity of the conjugacy, or
so no, but there is this heteroclinic tangencies, so which violates conjugacy. That is our rigidity result. That
I see.
Somehow, if there was such a conjugacy, then the average Jacobian should be equal. So that is but the question can be modified. So what happens when the average Jacobians are the same? So whether one can produce conjugate maps there.
So can you expect like finite codimension classes?
It is codimension one. Average Jacobian is just one parameter.
Yeah.
So you freeze this parameter. So if I codimension one submanifold, what happens there? It is a very natural question. It seems to be very difficult. I think that it would be very tremendously interesting to have some results in this direction. I don't anticipate that there would be a sort of topological conjugacy everywhere there, but there could be some results in this direction.
This is our result with Charles and Marco. So just to complement that, so in our work with Charles and Marco, we actually showed there are infinitely many moduli in arbitrarily close to the.
Even I cannot hear you, so.
Sorry, I was worried about putting it too close. So Yeah. So Charles and Marco now have this paper about infinitely many moduli in a,
So
close to
it is-
Feigenbaum in this small B strip.
Infinitely many moduli, so...
Yeah,
okay,
so we
what-
construct other invariants than just
So
the...
what are those moduli? So it is...
So the
some kind
moduli are like the Pallas invariants related
Pallas
to the...
invariants,
Yeah,
Okay, good.
For the odometer or for the global?
for the global situation.
But the restriction to the odometer could still.
So there is no recurrent dynamics. So for this zero entropy, in this zero entropy region, there is no much recurrence. You can still produce this kind of phenomenon.
If I remember correctly, yes.
Well,
but
Anyway, that is not the way we justified it. So, but we just analyze this heteroclinic loss and how they accumulate one onto another.
okay.
But maybe there is a different point of view. I just not aware of it.
Any more questions? Comments? No? Then let's thank Mich again.
Okay, thank you.